Okay, so now let us discuss insulation characteristics in the sense that what is the insulation level that I should decide? How do I decide on what insulation level I need to provide my insulation, and how do I decide whether it is reliable? What are the characteristics of the insulation that we should take into consideration during insulation coordination? So first let us talk about breakdown or disruptive discharge voltage. Now, what we have seen so far is that breakdown cannot be characterized by a single quantity. So when we say that the breakdown strength of air is 30 kV per centimeter, we are not really saying that you apply 30 kV per centimeter to air and it's definitely going to break down, or that if you apply voltages 20 kV per centimeter and weight, I mean a field strength of 20 kV per centimeter on air, and there will be no breakdown. That's not what we are able to say. But certainly we are able to say something with some confidence. And what is that? First, let us look at that. Now, obviously, since breakdown is a stochastic process, it is best quantized or best estimated through probability. So when I say that I am going to refer to the behavior of the insulation by its discharge probability, let's say I say PV. What is the probability of failure at voltage V? So that's the best I can do. I can only characterize the breakdown strength as a probability, or I can only characterize the behavior of the insulating material at a particular voltage by its probability of breakdown at that voltage. Now, generally, many processes or many probabilistic events can be characterized by a probability distribution function which takes the shape of a normal or Gaussian distribution. So, for example, in this figure, y-axis represents a probability density function, PF, and x-axis represents the variable f. It is a continuous variable. So PF is given by 1 by sigma root 2 pi e to the power minus fk minus ff whole square by 2 sigma square. What is fk? Fk is the probability of a certain event fk, a certain value of f equal to fk. The probability associated with that value fk is given by pfk, and the total distribution is given by pf as k varies from 1 to infinity or minus infinity to plus infinity. Minus infinity to plus infinity. F average is the average value of f throughout the distribution. Sigma is the standard distribution of the standard deviation of the distribution. So this is your probability distribution function of any random variable f. So if you transfer it to the voltage V, the breakdown voltage V, this is how I write it. PV is equal to 1 by sigma root over 2 pi e to the power minus V50 whole square by 2 sigma square. V50 is the voltage which has exactly 50% probability of failure. So the value of V for which probability is 50 is called V50. That's about the mean value, and sigma is, as before, your standard deviation. Now what I can say is, I cannot really say that breakdown, let's say this is the peak value, the peak of the probability distribution curve. Let us imagine this value is some value, let's say f equal to, let's say 30 kV per centimeter. So when I say that 30 kV per centimeter is the breakdown strength of air, let's say, I am not really able to say that if I apply 30 kV per centimeter, it will break down. I cannot say that with any certainty, because what might happen is breakdown might happen. Most of the times, maybe it will happen at 30 kV per centimeter. Here, 30 kV per centimeter is an arbitrary value that I have taken. It does not have any relevance as yet. I'm just talking about some arbitrary value, 30 kV per centimeter, air breaks down. It could be something else. Now, it is highly probable that at 30 kV per centimeter breakdown will happen. But it is also possible with quite a bit of probability that breakdown will happen at voltages lower than this. And as we go further and further to much lower values far away from 30 kV, the probability reduces. Similarly, there is a probability that breakdown will not happen at 30 kV and breakdown may happen at 40 kV, 45 kV. But as we keep going to higher and higher voltages, the probability of failure happening at those higher voltages and not at a lower voltage becomes low. So there is a mean value or a median value or a central value and or a most probable value, and the probability associated with that value is very high. So most of the time failure will happen at that value. But there is also considerable probability of failure happening at higher values or lower values which are centered around that value. So what I can say is this: I can define a quantity 1 minus lambda if, let me define a variable z where z is equal to v minus v50 by sigma. So this is of course derived from v, but it is convenient to use z for analysis. Now if I put z on the x-axis, then this maximum value v50 corresponds to z equal to 0. So z equal to 0 is the most probable value, and then I have z alpha by 2 values up to here and I put a mark here, and z alpha plus 2 on this side and put a mark here. So therefore this is alpha by 2, this is alpha by 2. So therefore the total area under this curve is 1 minus alpha. Now what I can say is that I know that this, let's say this z equal to 0 corresponds to 30 kV per centimeter. So 30 kV per centimeter is most likely, but I do not have any kind of guarantee. But I can say that I have a certain confidence. I can say with 1 minus alpha confidence that breakdown will happen within these limits. So therefore, I am more interested in the confidence interval. Maybe this confidence interval is something like 95% or something. So with what percent would I be able to say that my breakdown voltage is a particular value 30 kV centimeter? If I say, let's say I want to say with confidence interval of, I choose a confidence interval of 90%, let's say, which means if I choose 45% values on this side, so probability of 45% on this side, probability of 45% on this side, then the total area, such that the total area under this curve is 90%, then I will be able to say with 90% confidence that breakdown will happen at 30 kV per centimeter plus minus whatever values, plus minus this minimum value and maximum value. So I will be able to guarantee a range with a very high degree of confidence. So therefore the confidence intervals are of importance. So I might be talking about CFO. CFO is the critical flashover voltage, which has V equal to V50 or Z is equal to Z is equal to 0. This could be the critical flashover voltage if we are talking about flashover. It could be the critical disruptive voltage if we are talking about breakdown. And generally we work with CFO plus minus 3 sigma, sigma being the standard deviation. Apart from that, we define what is called the statistical withstand voltage. Statistical withstand voltage is that voltage which can be withstood with 13% probability. That means if I apply a very small voltage such that the area under this curve is only 13%, 0.13%, and the rest of the curve is 99.87%, then that particular voltage is called the statistical withstand voltage. You can imagine that it is a statistical voltage because it's a random process, and it is a withstand voltage because at that voltage, the breakdown probability is so low as to be negligible. How low is negligible? That we have specified. It is 0.13%. Similarly, we can talk about a statistical flashover voltage or a statistical disruptive discharge voltage, which is the voltage for which the probability of failure is 99.87%. Withstand, probability of withstand is only probability of withstand is very high. Probability of flashover is only 0.13%, whereas statistical flashover voltage, the probability of flashover is very high, withstand is very low, probability of flashover is 99.87%, probability of withstand is only 0.13%. So these are kind of certain parameters we work with. Now, apart from that, rather than the probability distribution function, we are more interested in terms of breakdown, we are more interested in the cumulative distribution function. Think about it like this. When I say air breaks down at 30 kV per centimeter, it means that if I apply a field of 30 kV per centimeter on air, it is not going to be able to withstand, it is going to break down. The chances are very high. Now, so let's say you apply 30 kV per centimeter and breakdown happens. Now, as an insulation engineer, are you really interested in whether the breakdown happens at 30 kV? Or if the breakdown happens at 29.5, whether it happens at 20, whether it happens at 10, no matter whether the breakdown happens at 5, 10, 19, 15, 20, any situation where the breakdown happens at a voltage either equal to or less than 30 kV centimeter is the same to me, because it gives me the information that air will not be able to withstand 30 kV per centimeter. And that is what I'm interested in. I'm going to apply 30 kV per centimeter, and I'm more or less certain that it's going to break down. And how certain am I? What is the probability that it will break down at 30 kV per centimeter? There is a particular probability associated with the value 30 kV per centimeter. Maybe it's 50%. So let's say it has a certain probability, 20%. But let's say the probability of breakdown at 40 kV per centimeter is another 20%. So what is the probability that as I increase the voltage from 0 to 30, breakdown will happen? If I only consider just 20 kV and 30 kV, the probability is 20% for 40 kV, 20% for 30 kV, that is 40 kV, 40%. So I have a 40% probability that air will not be able to withstand 30 kV per centimeter, because there is a 20% probability of failure at 30 kV. There is also a 20% probability of breakdown at 20 kV. So that's the point that I'm trying to make is that if my insulation will not withstand 30 kV per centimeter, I need to know what is the probability, what is the total probability of breakdown at any voltage lower than that, or at any field stress lower than that, which means I have to add up all the probabilities which are associated with all the values which are lower than 30 kV per centimeter. So therefore, instead of being interested or instead of characterizing the insulation breakdown with a probability distribution function, we will use a cumulative distribution function. The cumulative distribution function is given by capital P to differentiate it from small p. The cumulative probability of failure at voltage V is given by, as before, 1 by sigma root 2 pi integration. This is what is different. Integration minus infinity to plus infinity e to the power minus v minus v50 whole square by 2 sigma square. And if you express it in terms of the z variable which we had earlier mentioned, then pz is equal to 1 by sigma root over 2 pi integration minus infinity to z e to the power minus z square by 2 dz. So if you look at the cumulative distribution function for V, the Gaussian distribution, so this is V still follows a Gaussian distribution. So what happens is probability increases with voltage, reaches its maximum value, and then it comes down and reaches again a minimum value and trails to 0. But the cumulative distribution function never goes down, because the probability will keep on increasing as you keep on increasing the voltages. So there is some value you are increasing, and it has 30% probability, 40% probability, 50% probability. Ultimately, the probability becomes 1, which is a certainty. So there is a particular value of the voltage above which breakdown is a certainty. And the critical breakdown voltage is the value of the voltage. So we don't really work with this. The critical value of flashover or disruptive voltage is this V50. V50 is the probability, is the voltage for which the probability of failure is 50%. And now you must understand what I did not point out in the previous slide. When I'm talking about that voltage which has 50% probability of failure, it does not mean that there is a 50% probability associated with that particular value. It means that at values lower than that or equal to that, the total cumulative probability of failure is 50%. So as you keep raising the voltage, if you have a very large number of insulating materials, 50 of those will break down by the time you have approached this particular V50 value. But then there will be still quite a considerable number of samples which will not have broken down. But when you go to the steady state value, which is unity, then all of your samples will definitely have broken down and you have a certainty of breakdown. So similarly, here on this curve, which you can see what we have on the left hand side is PW, the Wheatstone probability, and on this side we have the statistical, this is a statistical Wheatstone voltage, and here we have the statistical flashover voltage. So as you see, this this value, this voltage increases, and with that the probability is increasing as a straight line, and then you have a value for which you have, let's say, 99.84 or whatever we said. So this value was 99.87 and 0.13. So this is the value for which you have 99.87. This is your statistical flashover voltage, and here you have 0.13%, which is your statistical Wheatstone voltage, and you can express this as a straight line. So we now therefore have the insulation characteristics expressed as not a probability distribution function, but a cumulative distribution function in terms of voltage. But remember, voltage is not the only thing that is of importance. Voltage determines the stress, but we have seen that failure is a function of the stress as well as the time to failure. So therefore, we should also have a probability distribution function for the time to failure. So for example, here I have written down the cumulative distribution function for the probability of time. P as a function of time, so this is cumulative distribution function of time, is also expressed as a normal distribution curve, 1 by sigma root 2 pi, integration 0 to t. So what is the cumulative probability of failure when you stress a material for t seconds? Is given by e to the power minus t by t bar whole square by 2 sigma square. T bar is the mean value of the time, and sigma is the standard deviation of the time. So time can be analyzed in treated in exactly the same manner as we have treated voltage, and we need to use these two factors together to completely define the insulation characteristics. So this is about distribution functions. Now let's say we have characterized our materials with distribution functions for voltage as well as time, and now I need to figure out an insulation level, which is the insulation level that I will provide my insulation with, which means my equipment will be designed to withstand such insulation level. So the insulation level is defined by the values of test voltages which the insulation of equipment under test must be able to withstand. So when you have a power transformer, there are some IEC standards or IEEE standards which specify the voltage level for every insulation that you provide with. So let's say turn-to-turn insulation, if you are talking about bushing insulation. So for every insulation, Depending upon the nature of the insulation, depending upon the kind of catastrophic failure, depending upon the ambience, application, etc., you have IEC standards which specify the insulation level. And as far as we are concerned, the insulation level is, while designing the insulation level, we have to design it in such a way that when you apply voltages or fills up to that level, that voltage level, it should be withstood. It should not fail under test. Now, in a subsequent chapter, we will talk about testing, which is also another thing. But let's say we don't bother about how we do the test. Let us just say that I have to provide my equipment with enough insulation such that it is able to withstand tests at that particular level. Standard insulation levels for all equipment have been arrived at in the standards. So for example, if you're talking about transmission line, when you have up to 245 kV, the tests are limited to lightning impulses and 1 minute power frequency test. I will not talk about this test right now. I will just talk about the lightning test. So if you're only testing for lightning impulses, it means that you expect that the lightning impulse will be the more dangerous. And that is natural because lightning is an external over voltage. It does not scale with the system voltage. But a switching over voltage scales with the system voltage. So when you are at low voltages, like up to 245 kV, if you design for lightning impulse, the switching impulses are automatically taken care of. So if your insulation is designed to withstand the prescribed tests levels for lightning impulse, then rest assured that they will be able to withstand the switching level tests. After above 300 kV, you will also have to test for switching impulses because switching impulses will become significantly high and can be more dangerous than the lightning impulses. In fact, you do not only test for simple switching impulses, you test for all kinds of switching impulses, which we will discuss in the next chapter. Now, once you have all these tests, you all these voltage levels, you select a suitable common BIL for all insulation. This is the basic insulation level. And this basic insulation level should be above the 50% flashover or 50% puncture voltage for all equipment. That means you are choosing a common, so you don't keep on choosing insulation levels separately for every equipment. You look at all the equipment, look at all kinds of clearances, what is the worst case scenario, and then you note down the 50% voltage for every equipment. And then your basic insulation level for your entire insulation level has to be a value which is equal to or higher than all the insulation levels of your equipment. After that, you have to choose adequate protective margin, which means if you want to protect for 300 kV, the insulation level has come out, let's say the basic insulation level has come out to be 300 kV. Then you have to provide a protective margin and provide insulation for 450 kV. Your protective devices will be set, so you then have to, so you choose an adequate protective margin, choose proper protective devices that provide good protection at reasonable cost. So cost is an issue. So you will set the protection level at a lower value than the insulation level so that there is a good enough protective margin. So taking all these things into consideration, you ultimately have been able to decide what level of insulation you require for your system. To give you an example of standard insulation level for a transmission line, let's say you have highest voltage for equipment is 300 kV. So let's say it's a 300 kV transmission line and you need to figure out what is the insulation level that you need to provide. Now in this case, longitudinal insulation needs a peak value of 750. Standard lightning impulse 750. Face-to-face ratio will be 1.5, so this is 850. Now this is, one is an IC standard, the other is an IEEE standard. So sometimes they match, sometimes they don't match. So this is also 750, they match, this is 850 already. So this gives you a value of 950. So the standard lightning impulse withstand voltage in peak terms for this 300 kV line, equipment for 300 kV line is not 300 kV, but 950 kV. And then, of course, you have to talk about protective margin and things like that. Similarly, for 362 kV, you arrive at a value like 1175 or 1050, depending on which standard you choose to follow. For 420, it's 1300. So as you can see, the voltage level and the voltage rating are quite different, and you're providing insulation for much higher insulation levels than your rated voltage. That is the point I wanted to make here. When you choose your protective device, to continue from what we have already discussed, the various equipment should have different volt time characteristics, because if you remember, some of them are more expendable and some of them are less expendable, in the sense that we would prefer some of them to be untouched. So naturally, the volt time characteristic of the lightning arrestor will be lowest. So if somebody has to go, it should be the lightning arrestor. The next thing is the transformer. That is why you will often hear of transformer blowing up. If there is a lightning strike, let's say, we would prefer it to be, if the lightning arrestor cannot prevent it, let it be on the transformer. We can take out the transformer, we can repair it, or we can put another transformer. And we would like a much higher protective margin for the line or for the bus bar. So the protective margin can be different for different parts of your network, depending upon which part you want to protect more or less.